This video is for those of you who are studying triple science and have been asking me, please can you make a video for the separate chemistry. So I've got a separate chemistry exam here that I'm going to lead you through. Don't forget to pause it on each question so you can have a think about the question first. So let's get started. In this video I'll be walking you through the 2024 separate chemistry paper. Question 1 is about making a salt, and this is a required practical. A student produced a salt by reacting copper carbonate with sulfuric acid. This is the method used. Measure 50 centimeters cubed of sulfuric acid into a beaker, add copper carbonate powder, stir the mixture, repeat steps 2 and 3 until copper carbonate is in excess, filter the mixture, warm the filtrate gently until crystals start to appear, and leave the solution to cool and crystallize. Question 1.1. Complete the word equation for the reaction. Copper carbonate and sulfuric acid, well, it's going to make copper sulfates, that will be a salt. We must remember that a carbonate and an acid makes a salt, and water and carbon dioxide. So water is the other product, and you can see carbon dioxide's already been written in for you. Question 1.2. Give one observation the student could make during step 4. So this is when they're adding copper carbonate until it's in excess. Well, one thing you could say is that once it's added excess, this fizzing is going to stop. So you could say the fizzing stops because we've used up all of the acid by adding excess carbonate. Or you could say that the solid remains, because to start with, as you add the copper carbonate, it disappears as it's reacting with the acid, but then when we've added excess, that copper carbonate is going to settle out at the bottom of the beaker. That would be the excess. Give one reason for filtering the mixture in step 5, that is to remove the excess carbonate. And remember, we added excess carbonate to ensure all of that sulfuric acid has been used up. Name the equipment that can be used to warm the filtrate gently in step 6. But we don't simply put it on a tripod and gauze. What we use is a water bath. And that could be an electric water bath, or more likely in your science lessons, you'll probably have a tripod and gauze with a beaker of water on top, and then your evaporating dish goes on top of that beaker of water, and that's all we mean by a water bath, and we'd heat that up with a Bunsen burner. The maximum theoretical mass of the salt that could be produced using 50 centimeters cubed of sulfuric acid is 12.5 grams. The percentage yield of the salt is 92.8%. Calculate the mass of salt actually produced. So we've got percentage yield is mass of salt actually produced divided by maximum theoretical mass times 100. So I've just simplified that a little bit here. Percentage yield is actual mass over maximum mass times 100. So let's put in what we've got. We've got the maximum mass is 12.5 grams. We're looking for the actual mass, and the percentage yield is 92.8. So if we start getting rid of some of these terms in the equation, we're going to have 92.8 times 12.5 is actual mass times 100. And then we need to get rid of this 100 on this side, so we do 92.8 times 12.5 over 100, so we divide by 100 on that side to give us our actual mass. And when we work all of that out, it comes to 11.6 grams. Some salts can be produced by reacting sulfuric acid with a metal. Neither copper nor sodium is used to produce a salt with sulfuric acid. Give one reason why each metal is not used. Well, first of all, copper is too unreactive, and that means it won't react with the acid. The reason for not using sodium is the opposite reason. It's near the top of the reactivity series, so this time it's too reactive, and that means it could explode, and it would certainly be too dangerous. This question is about the periodic table. Sodium and potassium are in group 1 of the periodic table. Give one similarity and one difference between the electronic structures of sodium and potassium. Well, one way you could do it is to quickly draw out the electronic structures. So if we draw sodium, we can see that sodium has got 11 electrons and potassium has got 19 electrons. So quickly, sodium has 2 in the first shell, then there will be 8 in the second, and that leaves 1 in the outer shell. Potassium has 2 in the first shell, 8 in the next, 8 in the next, and 1 in the outer shell. Now that's probably taken me 30 seconds, but it will ensure I definitely get the mark on this question, because we can now see at a glance they've both got 1 electron in the outer shell. And we can also see the difference is that sodium has 3 shells, whereas potassium has 4. There is another way you could have got to the same answer, and that is by looking at their position on the periodic table. So they're both in group 1 of the periodic table. So that means that they've both got 1 electron in the outer shell. Remember the rule that the group number tells you the number of electrons in the outer shell. So that tells us they've both got 1 electron in the outer shell. The other rule is that the period number tells you how many electron shells there are. So in this case, sodium is in period 3 because that's period 1, period 2, period 3. So that has 3 shells. Whereas potassium is in period 4, so that has 4 shells. Give 2 observations made when potassium reacts with water. Well, there's lots of things you can put here. You could put that it floats because it's not very dense. It fizzes because it's making hydrogen gas. You could say it moves around the water. You could say it produces steam because it's an exothermic reaction. So any of those would get you a mark each. Potassium hydroxide solution is produced when potassium reacts with water. What is the colour of universal indicator when added to potassium hydroxide solution? So you could have any colours like blue or violet, and the reason is potassium hydroxide is alkaline. That's why they're called the alkaline metals. Then we're given a set of data about the noble gases, their atomic number and their density. And we're asked to plot a graph. So I've already plotted the points, and when you're plotting these points you need to be accurate to within half a tiny square. So do be careful of what the scale is. So in this case the atomic number is going along in 2s along the bottom for each tiny square, and the density is going up 0.2 up the side for each tiny square. And then the other mark is for putting on a line of best fit. Notice how this straight line doesn't have to touch every one, and in science, remember, a line of best fit can be a straight line with a ruler, or it can be a smooth curve. The next question is estimate the density of krypton. Use figure 1 and table 1. So we need to use the graph and the table. So we're looking for krypton. So the first thing we do is we look on the table for krypton's atomic number, and it's 36. And then we use the ruler on the graph. So we're going to draw up from 36 until it hits the graph. And then we're going to read across from there. And that point on my graph is 3.8. So the answer here is going to be a density of 3.8. And on these, it obviously depends exactly where you've drawn that line. So the examiner will look at your graph and look at your answer, and there is a little bit of wiggle room either side of this answer. The elements in group 7 are called the halogens. A more reactive halogen can displace a less reactive halogen from a solution of its salts. Which combination of solutions will produce a reaction when mixed? So I'm looking for a more reactive halogen reacting with something that is less reactive, and we get chlorine and potassium bromide, because we've got chlorine here and potassium bromide. Chlorine is higher up group 7, so it's more reactive, so it's going to displace that bromide. Which of the following describes the trends going down group 7? So we've got molecular mass and we've got boiling point. We need to remember that as we go down group 7, the molecular mass is increasing, the atoms are getting bigger, and as that happens, the boiling point increases as well. So the one that shows that trend is this bottom one: relative molecular mass increases and boiling point increases. This question is about models of the atom. Figure 2 shows 2 early models of the atom. We've got model A, which is a ball of positive charge, and then we've got electrons dotted all the way through. And model B, we've got the positive in the centre, and then we've got electrons on shells. Well, model A is the plum pudding model proposed by J.J. Thomson, and model B is the Bohr model because it was a Danish scientist, Niels Bohr, who came up with the idea of electrons being on shells. Question 3.2 says compare model A with the model of the atom used today. So first of all, we can see there's no nucleus. So we can see model A has no nucleus. Today's atom does. We can also say there's no protons or neutrons in this model, whereas today's atom does. Now we know that today's atom, all of the positive charge is in a central nucleus, whereas model A has the positive charge spread throughout the entire atom. Finally, we need to talk about the electrons. Model A has the electrons spread throughout the atom, whereas these days we have electrons in shells. Chadwick's experiments showed the existence of neutrons in an atom. This led to an understanding of isotopes. Define the term isotope. Refer to subatomic particles in your answer. And this is a very common question on paper 1. So first of all, we'll say what's the same about atoms of an isotope, and that is they're atoms of the same element with the same number of protons. But what's different about them is they have different numbers of neutrons. A student investigated the energy change of the reaction between zinc and copper sulfate solution. This is the method used. Sometimes it helps if you draw it out as you're reading through. Measure 25 centimeters cubed of copper sulfate solution into a polystyrene cup. So we've got 25 centimeters cubed of copper sulfate. Measure the temperature change of the copper sulfate solution, so they'd be using a thermometer. Add 0.2 grams of zinc powder to the copper sulfate solution. Stir the mixture, record the highest temperature reached. Repeat steps 1 to 5 with different masses of zinc powder. And then we're presented with this graph of mass of zinc in grams and the highest temperature reached. And the next question is to draw 2 lines of best fit on here and make sure the lines intersect. So we can see it's a 2-part graph. The first part is where the temperature is increasing. So I'll draw a straight line there. And then there's this section here where the temperature is staying the same. And we can see the 2 lines are intersecting. The next question is explain the results shown in figure 3. Do not refer to any anomalous points and use data from figure 3. So we can see it's a 2-part graph. We've got this part here and then it changes here and we've got this part here. So I'm first of all going to explain why the temperature increase is more with the greater mass of zinc. So we're going to say as the mass increases, or the mass of zinc, we'll try and use what's on each axis, increases, the highest temperature reached increases. And we're going to say why the temperature increases, and it's because it's an exothermic reaction. Because it's an exothermic reaction. Then we need to say at what point it changes and why it's changed from this trend to this trend. And the point it changes is at 0.8 grams of zinc added, and that's because we've added excess zinc now. So all of the copper sulfate solution has been used up. So then I'm going to say once 0.8 grams of zinc has been added, the reaction stops as excess zinc has been added and the copper sulfate is used up. Then just for completeness, we'll explain this section of the graph and say there's no further reaction because the reaction has stopped. After this point, there is no further reaction. Explain why a polystyrene cup gives more accurate results than using a glass beaker. That's because polystyrene is an insulator, so that reduces heat loss or energy loss to the surroundings. Complete the ionic equation for the reaction between zinc and copper sulfate solution. So I've drawn out a few equations here to show you how we get to the answer. Here I've got the symbol equation, zinc and copper sulfate. Now zinc is higher up in the reactivity series, it's more reactive, so it can displace copper. So it forms zinc sulfate and copper is left on its own. We then look at where there will be ions, and ions are where you've got a metal with the non-metals. So we've got metal and non-metals here, so we've got copper ions and sulfate ions along with the zinc atoms, and on this side we've got zinc ions, sulfate ions and copper atoms. But you'll notice I've crossed out the sulfate ions because these are what we call spectator ions. They don't change between the start and the end of the reaction. So that leaves us with zinc atoms and copper ions, and on this side we're going to have zinc ions which will be dissolved in solution, so they will be AQ, and we've got copper atoms, and copper is a solid. If you want more help with ionic equations, I'll put a link up here now to one of my other videos with intensive practice on ionic equations. A different student repeated steps 1 to 5 of the method 4 times using 0.5 grams of zinc powder. Table 2 shows the results, and we've got 4 results here. Now when calculating a mean, the first thing we do is to see if there's any anomalies that we need to discard. But in this case there's no obvious anomalies, so we're going to use all 4 results. So to calculate the mean, we're going to do 37.6 plus 37.2 plus 37.6, sorry 37.8 that one is, plus 37.4. So all 4 of those, we're going to add them up first of all and then divide by 4, and that comes to 37.5. But it's also asking us to include the uncertainty in our answer. So 37.5 is our answer, and if we look at the lowest one below 37.5, it's 37.2 at the low end, and the highest one above the mean is 37.8. So we can see that is 0.3 lower than the mean, and this is 0.3 higher than the mean. So our answer is, the mean is 37.5 plus or minus 0.3 degrees. The results show random errors. The student did not make any measuring errors. So random errors are ones that can be either above the true value or below the true value. Suggest one reason for the random errors. So we can't say they've measured out, for example, the wrong mass of zinc. What we can say though is we know they stir in this. It might be they stir it a small amount one time and they stir it more the next time. So we can say different amounts of stirring. This question is about ionic compounds and electrolysis. Calcium chloride is an ionic compound. Calcium and chlorine react to produce calcium chloride. Describe what happens when calcium atoms and chlorine atoms when the ionic compound calcium chloride is formed. So the best tip for this is to quickly draw out the outer shell electrons of each. Now calcium is in group 2 of the periodic table. so it's going to have 2 electrons on the outer shell. Chlorine is in group 7, so chlorine is going to have 7 electrons on the outer shell. So we can now see that chlorine needs to gain 1 electron and calcium needs to lose 2 electrons. So that's our starting point. We're going to say chlorine atoms gain 1 electron, and we're going to say what type of ion they turn into. And at this point you need your periodic table, and a good tip that I always tell my students at the very start of the exam is to annotate your periodic table with the charges of ions. So everything in group 1 makes a 1+ ion, everything in group 2 makes a 2+ ion, group 3 make 3+, we miss group 4, group 7 make 1-, 2- for group 6 and 3- for group 5. So let's just recap. We've got 1+, 2+, 3+, miss it, 1-, 2-, 3-. So coming back to this question, chlorine atoms gain 1 electron. We look where chlorine is. It's in group 7 of the periodic table, so it's going to make a 1- ions. So we're going to say to form Cl- ions. Then we're going to talk about what the calcium atoms do. We can see they need to lose 2 electrons. So calcium atoms lose 2 electrons to form. So let's have a look where calcium is. Calcium is in group 2, and we now know that's going to make 2+ ions. Ca2+ ions. And the last mark, which is the one that's more challenging, is to explain how this is going to work, because calcium needs to lose 2 electrons, chlorine needs to gain 1. So this calcium atom will give 1 electron to that chlorine, but now that's got enough. So what it takes is another chlorine atom with 7 electrons to take the other electron from calcium. So we're going to say each calcium atom reacts with 2 chlorine atoms. So the 2 chlorine atoms can accept the 2 electrons from the calcium atom. Solid calcium chloride cannot be electrolyzed. Give one reason why. That's because the ions are not free to move. So that's because the ions are held in that giant ionic lattice. The only way you can get ionic substances to conduct electricity is to turn them into a liquid so the ions are free to move, and that would involve melting the substance or dissolving it in water. Name the product formed at the negative electrode when aqueous calcium chloride is electrolyzed. So what I would normally suggest here is to draw a quick sketch of the electrodes. We've got positive anode here, and then we've got the negative cathode. And if it's calcium chloride solution, we've got those Ca2+ ions. We've also got those Cl- ions, but this word solution changes everything because it's in water. So the water itself also ionizes to form hydrogen ions and hydroxide ions. And the question's asking at the negative electrode. So the negative electrode is going to attract the positive ions, in this case calcium and hydrogen. And the rule for the negative electrode is the least reactive one will be discharged and produce something. So out of calcium and hydrogen, hydrogen is the least reactive one, so it's hydrogen that is produced. What is the half equation for the reaction at the positive electrode when aqueous calcium chloride solution is electrolyzed? Well, if we bring back my working out diagram here, we can see at the positive electrode it's going to attract the chloride ions and the hydroxide ions. And the rule for this side is if we have a halogen, that will be discharged, or a halide ion. If we haven't, then oxygen will be made. Now in this case, we have got a halide ion moving towards there, so it's the halide ion that's going to be discharged. So in this case, chloride ions will make chlorine. So it has to be this one because it's the chlorine one, and in electrolysis, ions change into atoms. A student investigated the electrolysis of green copper chromate solution. We've got a power supply, positive and a negative electrode. This time we've got filter paper soaked in the electrolyte solution, and we've got a drop of green copper chromate solution placed on the filter paper. And then we've got a picture of the results. So after it's been left a while to work, it separates into two colours. We've got a blue colour moving over here and a yellow colour moving over here. And the question is, copper chromate solution contains the ions Cu2 plus and CrO4 2 minus. So that's the copper, that's the chromate. So I'm going to do the answer on here just so that you can relate it to the results, but obviously you'd write it on the lined part of your paper. So we've got copper ions and we've got those chromate ions, and we've got to remember during electrolysis opposite charges attract. So the negative electrode is going to drag the copper ions that way, and the positive electrode is going to drag the chromate ions this way. Okay, so the reason we get that blue colour is because copper ions are blue and they're being attracted to the negative electrode. They are attracted to the negative electrode. And then at this side, these chromate ions are negative, so they're being attracted to the positive side, and they're yellow, those chromate ions. So chromate ions are yellow and they are attracted to the positive electrode. So this really shows what electrolysis is. Electrolysis means using electricity to split something apart. So we started off with a splodge of copper chromate, and it's splitting the copper one way and the chromate the other way. A student investigated the voltage produced by different pairs of metal electrodes in a chemical cell. So we've got nickel and another electrode in 1 mole per dm cubed sodium chloride solution, and we've got a voltmeter measuring the potential difference produced. So this is what they did. Place a nickel electrode and an electrode made from a different metal, which is electrode A, in 1 mole per dm cubed sodium chloride solution, measure the voltage and repeat with different metals. And then we've got a table of the results obtained. Now what we need to remember for this is if we've got the biggest difference in reactivity between nickel and this other electrode, it will give us the biggest voltage. So the bigger the voltage, the bigger the difference in reactivity. And the next question says, write the symbols of the 5 metals in the table in order of reactivity. So if I just have a look at the table and write it next to it so that we can see what we're looking at, it's going to be magnesium first because that's got the highest voltage. Then the next highest is going to be zinc, as that is 0.5. Then we've got nickel, which is 0. Then copper, which is minus 0.59. And finally silver, which is minus 1.05. And our justification for that is the higher the voltage produced means it's more reactive. So the higher voltage there with magnesium and the lower voltage there with silver. The voltage produced by a chemical cell depends on the concentration of the electrolyte solution. Plan an experiment to investigate how the voltage produced by a chemical cell varies with the concentration of the electrolyte solution. The following substances are available: the metal electrodes in table 3, 1 mole per dm cubed sodium chloride solution, and pure water. So first of all, we set up the cell with 2 different electrodes. And I'm going to choose the one that gave me the biggest voltage. So that would be magnesium and nickel. Then going to start with the 1 mole per dm cubed solution and record the voltage. Then I need to get different concentration solutions, and I can do that by diluting this down with pure water using a measuring cylinder. So using a measuring cylinder, use the pure water to dilute the 1 mole per dm cubed solution to obtain different concentration solutions. So that's how I get my different solutions with different concentration, by essentially watering down the 1 mole per dm cubed solution that we're given. So then I'm going to repeat the experiment using different concentration solutions, but I need to keep the volume the same, but keep the same volume of solution, and I also need to keep the same combination of metals for the electrodes. Describe how a hydrogen fuel cell produces a potential difference. Well, hydrogen loses electrons, or you could say is oxidized, because remember, oxidation is loss of electrons, and when it does that, in the end it forms water when it's reacted with the oxygen. This question is about iron. Iron is a metal. Describe how iron conducts thermal energy. Well, first of all, we need to mention those delocalized electrons. So we say it has delocalized electrons, and it's those that transfer the thermal energy through the whole structure. These transfer the thermal energy through the whole structure. Pure iron is too soft for many uses. Explain why mixing iron with other metals makes alloys which are much harder than pure iron. Well, I'm going to draw a couple of diagrams to remind you about the difference between pure iron and an alloy. So we can see with pure iron, we've got the same sized atoms. That means they're capable of sliding past each other, so it makes the iron soft. Whereas an alloy, we've got different sized atoms. This distorts the layers and locks them in place so they can't slide past each other. So for our answer, we need to say an alloy has different sized atoms. That distorts the layers. And that means the atoms can't slide past each other. When iron reacts with chlorine, 0.12 moles of iron reacts with 0.18 moles of chlorine. What is the correct equation? And we know for 1 mark, we're not going to be asked to work out some complicated moles answer. So we just need to spot the ratio. That's 12 to 18. And if we divide each side by 6, that means it's a ratio of 2 to 3. Okay, so the only one that's a ratio of 2 to 3 is this one here. This one's a bit trickier. What is the ratio of numbers of ions in Fe3O4? So we've got 3 ions and we've got 4 oxide ions. Now we know that the oxide ions are going to be 2 minus. So whatever Fe ions we've got need to add up to 8 plus to balance out the 8 minus. If we had 3 Fe3 pluses, that would be 9 plus. 3 of those would be 6 plus altogether. So it's going to be this one, because if we've got a 2 plus and 2 3 pluses, we can see there we've got 8 plus here and 8 minus there, so that cancels out. Calculate the percentage mass of iron in Fe3O4. So first of all, we need to work out the MR of the whole molecule. So Fe3O4 is going to be, we've got 3 lots of iron, so it's going to be 3 times 56 added onto 4 lots of oxygen, 4 times 16, and that is 168 add 64, which is 232. So Fe3O4 has a formula mass of 232. Now the iron part of it, we've got 3 irons, is going to be 3 times 56, which is 168. So we want to know what is 168, the iron part, compared to the whole formula. So we do the small number, which is 168, divided by the big number, 232, times 100 to get it as a percent, and that comes to 72.4%. Fe2O3 reacts with carbon to produce carbon dioxide. Here's the equation. Calculate the volume of carbon dioxide gas at room temperature and pressure that is produced from 40 kilograms of Fe2O3 using excess carbon. The relative formula mass of Fe2O3 is 160, and the volume of 1 mole of any gas at room temperature and pressure is 24 dm cubed. So the bits that we're interested in is 2 Fe2O3, and that forms eventually 3 CO2. So it's a ratio of 2 to 3. So the first thing we need to do is work out how many moles of this we've got, because 2 moles of this will make 3 moles of that. So we've got 40 kilograms, which is 40,000 grams. We times the kilograms by 1,000. So remember, moles equals mass over mR, which is going to be 40,000 divided by 160, so that's 250 moles. Now we've got to remember the ratio is 2 to 3. So if we divide it by 2, that becomes 1 to 1.5. So the number of moles of this is 1.5 times more than the number of moles of this. So we've got 250 moles of Fe2O3. So that tells us if we times that by 1.5, we're going to get 375 moles of CO2. Now we know that 1 mole is 24 dm cubed in terms of volume. It tells us in the question 1 mole equals 24 dm cubed. So to get the volume of carbon dioxide, we just times the number of moles by 24. So the volume of CO2 is 375 times 24, which is 9,000. This question is about propane. Figure 7 shows the displayed structural formula of propane. And then the question says, explain why propane has a low boiling point. Well, it's because it's a simple molecule, or you could say a small covalent molecule, and they have weak intermolecular forces. That means forces between the molecules are very weak, and they don't need much energy to break those forces. So as soon as you start putting some energy in, the forces break and the particles move apart, so those turn into a gas. Propane reacts with oxygen to produce carbon dioxide and water. The reaction is exothermic. Figure 8 shows 4 reaction profiles, and we need to choose the right profile with the right labels. And if it's an exothermic reaction, we know that energy is being given out to the surroundings, so the energy level of the chemicals is going to go down. So we're looking for ones where the energy level of the products is lower than the energy level of the reactants. So it could be one of these two. It can't be that because that's endothermic, and that's also endothermic. So then we need to look at the labels. The overall energy change isn't that bit there, it's between the reactants and the products, so this is the correct label, so B is the correct reaction profile. Figure 9 shows the displayed formula equation for the reaction between propane and oxygen. There's propane, there's oxygen. The overall energy change of this exothermic reaction is 2219 kilojoules per mole. Table 4 shows the bond energies of the bonds in the reaction. So what we need to remember is that the bonds broken over on this side of the arrow minus the bonds made on this side of the arrow equals 2219 kilojoules per mole. Now because it's an exothermic reaction, that's going to be negative. So bonds broken take away bonds made is minus 2219 kilojoules per mole. So the first thing I'm going to do is on this side write down the bonds broken, and on this side the bonds made. And it's worth ticking off the bonds as you go along. So first of all, I've got 2 C to C bonds. I've also got 1, 2, 3, 4, 5, 6, 7, 8 H to C bonds. And I've got 5 O to O bonds. And on this side, I've got 6 C to O bonds. I've got 8 H to O bonds. Then I'm going to use the table to fill in the bond energies. So C to C is 347, so that's 347 times 2. Then I've got H to C times 8. Now we don't know what that is. We're trying to work out that bond energy. That's the whole point of the question. So whatever X is times 8, and we've also got 5 times 498. And we're going to call that total Y. On the bonds made side, we've got C to O times 6, which is 805 times 6. We've also got H to O, 464 times 8. So that comes to 4830. This comes to 3712. So the total for bonds made is 8542 kilojoules per mole. So coming back to this, bonds broken take away bonds made is minus 2219 kilojoules per mole. So this value here for the bonds broken, which I'm calling Y, Y minus 8542 equals minus 2219 kilojoules per mole. So to get rid of this, we need to add 8542 onto each side. So Y then becomes minus 2219 plus 8542, which is 6323. So remember what we've got for Y here. We've got 347 times 2, which comes to 694. We've got 498 times 5, which is 2490. So on this side then we've got 694. So instead of Y we're going to have 694 plus X times 8, this bond that we're trying to find, plus 2490 equals 6323. So to get rid of these terms, we'll first of all do 694 plus X times 8 is, we take that off both sides and that becomes 3833. Then we take 694 off each side, so we're left with x times 8 is, and take 694 off there, 3139, and then we need to divide it by 8 to find what x is, that bond energy, and that is 392.375. So call it 392 kilojoules per mole. This question is about acids and their reactions. Acids can be either weak or strong. What is meant by a weak acid? Well, it's one that only partially ionizes, or you could say partially dissociates, and that's when it's in aqueous solution. Explain what happens to the pH of an acid as the acid is diluted with water. Well, first of all, the concentration of hydrogen ions decreases by adding more water. And if the concentration of hydrogen ions decreases, that means that the pH will increase. A student does a titration to find the volume of acid needed to neutralize an acid. The student fills the burette with the acid. Give 3 more steps the student must do before adding the acid to the alkali. So first of all, we use the pipette to put the alkali in a conical flask. We then add indicator and we place the flask on a white tile so that you can see the colour change. You could also say take the start reading of the burette. The student titrated a solution containing 0.0045 moles of sodium hydroxide with 0.15 moles per dm cubed hydrochloric acid. So that's the concentration of the hydrochloric acid. Here's the equation for the reaction. So it's telling us we've got 0.0045 moles of this, NaOH. So because it's a ratio of 1 to 1, we'll need 0.0045 moles of hydrochloric acid to exactly neutralize it. Now, concentration equals moles divided by volume in dm cubed. So if we rearrange that equation, the volume in dm cubed equals moles over concentration. So the volume then in dm cubed is going to be 0.0045 divided by 0.15, which is 0.03 dm cubed, and to change it to cm cubed we need to times it by 1000, which is 30 cm cubed. So that is going to be our answer, 30 cm cubed. And finally, on to the last question. Well done if you've stuck with it by now. A calcium atom is larger than a magnesium atom. Explain why calcium reacts more vigorously than magnesium with hydrochloric acid of the same concentration. So it's really saying, why is calcium more reactive than magnesium? They're both in group 2. They've both got to lose 2 electrons. So we can say that calcium is a bigger atom, or it's got a larger atomic radius. That means the outer electron are further from the nucleus. That means there's going to be less attraction on those electrons by the nucleus. So less attraction between the nucleus and outer electrons that it's trying to lose. So that means it's easier to lose those electrons. If you found this video useful, don't forget to like and subscribe. Tell your friends about my channel. Thank you for watching.